Okay, I know a lot of you have already been working on these two sections, 10.3 and 10.4, but I wanted to go over a little bit of things with you just to solidify what you need to know for this chapter. Okay? The F distribution is what sections 10.3 and 10.4 are about. Mostly 10.3, F distribution. I gave you the F distribution table the other day. Does everybody have that still? Okay. You will definitely need to be able to refer to the F distribution table. Here's mine right here. The thing I want you to be able to recognize is when you first look at it, they all pretty much look exactly the same. What's the difference? Level of confidence at the top. Okay. At the top of each section tells you the level of confidence. Just look for the correct level of confidence. And am I saying the right word? Yes. And then use that particular page for your degrees of freedom for your numerator and your denominator. Okay? So a couple things. First of all, there's several properties about the F distribution that I want you to know. First of all, F distribution is a family of curves. Okay? Family of curves in which each is determined by two types of degrees of freedom based on the numerator and the denominator. That it corresponds to the variance of each of those. Okay, F distribution is positively skewed and therefore it is not symmetric. Okay, positively skewed, so the bigger part is here at the beginning. Okay, the total area under an F distribution curve is equal to 1. So that's like a standard normal curve that is symmetric. Okay, but this one is not symmetric, but its area underneath it is still equal to 1. All values of F are greater than or equal to 0. So all F values are positive. Okay, for all F distributions, the mean value of F is approximately equal to 1. All right? Okay, so that's some of the first things I need you to know. Of course, all the same guidelines I put on your formula chart, so you can just go through and look at those. But this one specifically talks about finding a critical value for an F distribution, which is pretty important. Okay, first of all, I need you to know that dF sub n stands for degrees of freedom of the numerator. Okay, they don't really type out degrees of freedom for the numerator. They type out this symbol. Okay, same thing for denominator, degrees of freedom for the denominator. Using table 7 in the appendix, which is the table I just showed you, to find the critical values. So when the hypothesis test is one-tailed, use this F table, just as it tells you to. Okay, if it's two-tailed, you've got to find not the one that's given, but half of it, right? Okay, I actually did a problem the other day and I couldn't find the answer because it was supposed to be 0.01 level of confidence, except it turned out I was looking at the wrong table because I forgot to think, oh my gosh, this is two-tailed, it's equal, so I got to use half of that. I had to use this one. Okay, so just be real careful of that, is all I'll caution you for that, okay? Note that because F is always greater than or equal to 1, all one-tailed tests are right-tailed. Okay, for two-tailed tests, you only need to find the right-tailed critical value. All right, so even if it's two-tailed, we're still only finding that right value. Does that make sense to everyone? Okay. Two sample F tests. Okay, two sample F tests is used to compare the population variances in obviously two samples. That's what's called the two sample F tests. Okay, but before you can even perform this test, you have to make sure 3 things are true. First of all, the samples have to be random, the samples have to be independent of each other, and each population must have a normal distribution. Now, I don't want this to be tricky, okay, but it might be if you're not paying attention, because I know one of the questions on the homework asks you what are the 3 things that have to be true, and 2 of them are really close. 2 of the selections are really close. Random and independent's pretty obvious, but one of the selections says the population must have a normal distribution, and the other one says the sample must have a normal distribution. Okay? The random and independentness has to be the samples that you've taken. The population has to have a normal distribution. Does that make sense? So just don't let it trick you. Just know it. Fair? All right. Sample 1, sample 2 with variances. Sample 1 is going to be bigger. Okay? Why? Because we need sample 1 to be bigger. So if we divide a smaller number by something, we're going to get something less than 1, right? And what do we know about our f values? They're going to be greater than or equal to 1. Okay, so our samples right here, the bigger one has to be sample 1. We put the bigger one in the numerator when we're dividing to try to find f. Okay. There's guidelines for using a two-sample test to compare the two variances. This again a good guideline to follow. I would like to walk you through this example right here. Okay, example number 3. A restaurant manager is designing a system that is intended to decrease the variance of time customers wait before their meals are served. Under the old system, a random sample of 10 customers had a variance of 400. Under the new system, a random sample of 21 customers had a variance of 256. At a level of confidence of 10%, is there enough evidence to convince the manager to switch to the new system? Now, you know, part of my trouble with some of this stuff is it's not real. It's all made up numbers. We just do a whole bunch of calculations. Guys, this is real. Managers do this. Business people do stuff like this, don't they? Okay? So, because 400 is greater than 256, our sample 1 is going to be 400 and our sample 2 is going to be 256. So, first of all, we have to figure out the null hypothesis and the alternate hypothesis. Okay? Well, why do you think they chose these? Why do we not choose equal? If these times are equal, does the manager need to switch? No, we want to know when the second variation is less. Okay, that's the null hypothesis. The claim is that the second variation is more. It's faster. Okay. So note that this is a right-tailed test with a 10% confidence. Degree of freedom, well, how many samples were there for my numerator? Well, there was 10 customers and 21 customers, right? So my numerator is going to be 10 minus 1, because we know degrees of freedom is n minus 1, the number of in the sample size minus 1. Okay. And then my degree of freedom in my denominator is going to be 20 minus 1. So that's 20. Sorry. Okay. So we check out this degree of freedom table. We're looking on the 10% one, which is right here. Our degree, what did we say our numerator was? 9, and denominator is 20. So go over to 9, come down to 20, 1.96. Not hard, right? Okay, so 1.96 is my critical value, my f sub 0. Okay, doing the actual division gives me my f value, not my f sub 0. F sub 0 is my critical value. I found that 1.96. That gives me my critical value to know where to look. Okay, doing the actual f division, the 400 divided by 256 gives me 1.56. Well, is 1.56 in this area right here, or is it in the rejection region? Well, 1.56 is less than 1.96, so it's not in the rejection region. So, what do? You fail to reject it. If it's not in the rejection region, you fail to reject it. Okay? There's not enough evidence at 10% level of significance to convince the manager to switch to a new system. Does that help? Does that make sense? Okay, so these were my personal notes for this section. Remember that degree of freedom of numerator, that's the notation for that, and denominator, the notation for that. For two sample F tests, you've got to have 3 things. They have to be random. The sample has to be random and independent, and the population has to be a normal distribution. Okay, be able to read your F table, and then be able to find F. How do you find F again? The variance of sample 1 divided by the variance of sample 2. Got that? Okay, so that's 10.3. 10.4, here's my notes for 10.4. Okay, has to do with ANOVA tests, one-way ANOVA tests. Okay, in an ANOVA test, this is my favorite part. The null hypothesis is always the same, and the alternative hypothesis is always the same. Okay, in an ANOVA test, the null hypothesis is always that all of your samples are equal. Always. Okay? Alternative hypothesis is at least one of them isn't. It's not that they all have to be not equal, it's that at least one of them isn't. Does that make sense? Okay. Degree of freedom of numerator. We still have the same sort of notation, but this time they mean something differently. Okay? Mean something different, not differently, sorry. Degree of freedom of the numerator this time is going to be k minus 1. So k is going to be the number of samples that you have. How many samples, how many possibilities do you have? Make that minus 1. Degree of freedom of the denominator is going to be the total, the sum of the sample size minus how many samples you have. Okay? F sub 0 again is going to come from the table. I'm going to show you how to do F in the calculator because you can get F in the calculator. The thing is, time-wise, you can do F in the calculator and you can also do all of this stuff down here. Here's how you get F, but to know those, you have to know those, and to know those, you have to know these and these. Okay? Time-wise, they're almost the same though. Okay? I want to talk through this example with you to make sure that you know how to do all this stuff and understand what they all mean, and so I can show you how to do it in the calculator. Okay? So, it's talking about medical researcher wanting to determine if there's a difference between mean lengths of time that it takes for three different kinds of pain relievers to provide relief from a headache. Okay? So first of all, this is the kind of information that they'll give you. They'll give you the n, they'll give you the mean of the sample, and they'll give you the variance. Okay? So I'm going to make a new document. No, I don't want to save the old one. I'm going to zoom in so you can see what I'm putting in a little bit. Okay? I'm going to make a list and spreadsheet. On my list and spreadsheet, I'm going to enter these things right here. Now, when I did this the first time, this is me learning about the calculator as you are. Okay? I put in medication 1, 2, and 3, so I just put in 1, 2, 3. I'll tell you this right now, the calculator does not like that. It does not like for you to name columns numbers. Okay? So I had to go back and name them X, Y, and Z, or med 1, med 2, med 3, or something like that, but don't just put a number. It does not like that. Okay? So I'm going to enter all the values, 12, 15, 17, 12, 16, 14, 21, 15, and 19, and 14, 17, 20, and 15. I'll go over here to the side, not there, right there. And I'm going to hit Menu, Statistics, Stat Tests, and then if I hit the up arrow, it's faster because it's right down here at the bottom, ANOVA, right there. Okay? Now, how is it wanting the input? Is it data or just statistics that I put in? Well, it's data. I put in all the tables, right? So I leave that there. How many groups are there? How many types of medication do I have to choose from? 3. So that's going to be a 3. Okay? Well, what did I call list 1? I called it X. I called list 2 Y. And I called list 3 Z. Where do I want my results? It says E. That's probably fine. I just don't want it in A, B, or C. Okay? So it tells me right there what my F value is. If I hover it over, you can't see. F is right there. Okay? Of course, there's a whole lot of other stuff down here if you go look, just like there always is. But if all you're trying to find is your F value, there it is right there. Okay? Now, how are you going to find your F sub 0, your critical value? The table. Yeah, the table. Okay? I need to let you know, though, if you are on a calculator page and you say Menu, Statistics, Stat Tests, and ANOVA, there's supposed to be a way that you can just enter statistics like this. I want to show you 3, and then since we're given all this stuff, there should be a way for us to enter this right here. For whatever reason, we cannot get this to work right now. Okay, because this would be so much easier, wouldn't it, than putting all those values in the table. Every single time I do it, it tells me my argument must be a list. And I don't know enough about this calculator yet with statistics to know how to fix that. Okay? I'm actually going to probably go call TI Cares. They have a little hotline for educators who are messing up on the calculator and they can fix it. Okay? I was going to go call them and find out what to do correctly so it will work. Okay, so I may tell you in the next couple days about that to show you how to fix that. But right now, there is a way. I can't figure out how to work it. Okay. So just to let you know, when they did their F value, they got, whoops, you can't see it. When they did their F value, they got 1.5, which is what we got in the calculator. So it is an appropriate way than having to do all this math right down here. Okay, which is fine. We're just using this as a tool to get where we need to get faster. Okay. Do you have any questions? Okay, those are all the notes that I have for this, for 10.3 and 10.4. If you have any other questions, please, please, please come and ask. Okay? Oh, one more thing. I do have one more thing. See my star right down here? Your rejection region is going to come from your critical value. Okay? So if we're looking at this graph right here for the problem that we just did, where did this 7.56 come from? That came from our F table, right? That's our F sub 0. So if I'm saying, where is my rejection region in relation to 7.56? It's greater than 7.56, right? My rejection region is on this side. So keep in mind, where's your critical value and where's your rejection region in relation to that? That's a good question. I think the answer to that is yes. Okay? Because we're always looking for, because of the way it's skewed to begin with, we're always looking for the right. Okay? And there was one more thing that got asked earlier. Dang, dang, dang. I was trying to remember to tell you. I'm not going to remember to tell you, so I'll have to tell you later. I'm sorry. It had to do with that problem. What was it about? Nope, not going to remember. Work on this. I'll see if I can remember, and then I'll tell you here in a little while, okay? Any questions?